Welcome, everybody. Thank you for joining our talk today by Volodymyr Kuleshov. And before we'll start this exciting talk, I'll let my colleague Marta to make some brief explanation of our initiative, AI Helps Ukraine. Word to you, Marta.
Thank you. I'm just going to share some slides before. Okay, so hello everyone. Thanks for joining us today. My name is Marta and I'm one of the team members of AI Helps Ukraine. And I'll just take 3-4 minutes to briefly explain to you what AI Helps Ukraine is. So AI Helps Ukraine is a charity conference on AI organized mainly by students and mainly by students from Mila. And it aims at fundraising money to send medical and humanitarian aid to Ukraine. So these are some of our speakers. Oops. So today we're especially excited because this is our last online talk. We're closing the conference with Volodymyr Kuleshov. But before we had multiple awesome online talks during October, November, and December. And we also had an in-person event last week at Mila. Here are some of the pictures of our in-person events. If you missed it and you couldn't come, don't worry. We uploaded all the registrations from the videos to our broadcast profile. However, I'd like to take some time to explain why we decided to organize AI Helps Ukraine. So it's been 10 months since the Russian invasion of Ukraine began, and the level of death, destruction, and suffering inflicted on the civilian population is beyond any comprehension. No one in Ukraine is left unaffected by this war. These are just normal people like you and me who are living their lives, bringing their kids to school, and going to their offices to work, meeting friends in cafes, having normal lives until the 24th of February this year. During these latest weeks, some of our Ukrainian team members have been doing this brief introduction, showing pictures of the places where they used to play basketball or cities where they come from with destroyed buildings, roads, or playgrounds. We could have even shown harder pictures of human horror. There are many of them. I'm not Ukrainian, but I have been following very closely the armed conflict due to my personal ties with Ukraine. And I know and I've been to some of the places that we now see destroyed in the news. I've heard from very close people how horrible the situation is and how brave Ukrainians are. So the war is still ongoing in Ukraine and multiple basic infrastructures have been damaged. People can hardly access to electricity. And right now the temperature in Kiev feels like -3 degrees and it was snowing today. Indeed, Ukrainian winter is very similar to the Canadian one. If you are based here in Canada, you might be able to understand how challenging it can be to not have heating during the winter. Or some people cannot work and they don't have access to basic necessities, for instance. So we decided to start this conference because we believe that us as human beings, we cannot be indifferent to human suffering and injustices. Most of us have special ties with Ukraine, and the seeds of this conference started when one of our team members learned that one of her friends who had cancer, she had to leave the country because she couldn't receive the cancer treatment that she needed. So we contacted the National Cancer Institute in Ukraine, which sent us a list of the main items needed, and who we interviewed, and you can watch the interview that we made on our website or on our YouTube channel. And we also created a partnership with UAMS, Ukraine Medical Support, which is a nonprofit Canadian organization with a huge expertise in sending medical and humanitarian aid from Canada to Ukraine. And both of them confirmed us what we already knew, that the needs are immense and that every help matters. So this is an example of how each donation has a real impact. If you donate $20, you can think that that's not a lot, but indeed it is. $20 means a food of basket full of basic items that can be very, very useful for a family of 4 people for a couple of days. And if 120 people donate $20, that's $2,400. And that's the price of this device on the left side of the image. This is a device in a very high demand currently in Ukraine because it allows to heal wounds from missiles as well. And as we all know, Russia is very commonly shelling civil zones, or civilians can get hurt from missiles on the ground. So without these devices, the injuries quickly get infected and the consequence of that can be disastrous. So we're trying to give a last push to our fundraising campaign and overpass $10,000 by this week and maybe get to 12 or 13,000 by next Thursday, that we will close the fundraising. So please make your contribution and help us to get farther with every donation, no matter how small it is. We're also organizing an auction on Twitter. You can participate to win a deep learning book signed by Joshua Bengio and Aaron Corville. As always, all proceeds will be used to send medical and humanitarian aid to Ukraine. So I invite you to participate during this week. It will finish next week on the 21st of December. And so the biggest power is in unity. And our team strongly believes that the collective efforts of our broad international community can make a real difference for those who are in need. This difference can become broader with every donation, with every retweet, with every share of our posts on social media, etc. And since this is our last talk, I want to give a big thanks to all those who have participated in the organization of the conference and to all volunteers that have made it possible. To Alexandra for coming up with the idea, and to her and Alexi for taking the first steps to start the conference. A big thanks to all our great speakers who have kindly accepted to dedicate some of their precious time to us, and who some of them made very generous donations. And a big thanks to you, to all those who are listening to us right now and that participated in the conference and that made a contribution. And last but not least, I'd like to especially thank our partners, Mila Quebec AI Institute, who has helped us with the logistics, venue and promotion, Ukraine Medical Support, and Google Montreal, who has sponsored the conference. And after these long 3 minutes, I give the floor to Dima, who will briefly introduce our speaker of today. Thank you very much. Dima, we cannot hear you. No, we cannot hear you.
Yeah, then let's introduce our next speaker, maybe without Dima. So our today's speaker is Volodymyr Kuleshov. He's a professor at Cornell Tech. He works on applications of machine learning in science, health, and sustainability. And we're really happy to welcome you. Without further ado, I think, Volodymyr, you can start sharing your screen, and the floor is yours.
Thank you. Thank you. And can I check if you can see my slides right now?
Yes.
Okay, great. And you see them full screen, right?
It's perfect.
It's perfect. Okay, great. Thank you. Okay, well, thank you for inviting me to give this presentation. I'm really happy to be here. And I also want to just mention that I'm really grateful for the organizers for creating this event. I think that helping Ukraine right now is really, really important. I myself am originally from Ukraine, and I still have a lot of friends and family members there. And I'm really grateful to the organizers for inviting me and for giving me the opportunity to also help in some way to help Ukraine and to contribute to the effort and all the work that they're doing towards this right now. So the title of the talk is a little bit more, and the title and the contents of the talk will be a little bit more technical. So the title is Uncertainty-Aware Machine Learning for a Sustainable Food Supply Chain. The organizers mentioned that, or they suggested that I do a presentation on an application of machine learning to social good. And this will be the overall theme of the presentation. Part of the talk will be about some interesting technical ideas in machine learning around uncertainty estimation. And another part of the talk will be about applying these methods to what I think is a really important problem in sustainability, specifically the problem of reducing food waste. So those are going to be the two main themes of the talk. And I'd like to start by just a few words about myself and my background. As you just heard, I'm a faculty member at Cornell Tech, which is a campus of Cornell University in Manhattan. Here you see a picture of our beautiful campus. Cornell Tech was a campus that was created to focus particularly on applied research in science and technology, as well as on the translation of this research to real-world problems, to problems that are important to society. And in addition to being a faculty member, I'm a co-founder of a company called Afresh, which is a company that came out of some of my PhD research at Stanford. And this problem is using some of the machine learning technologies that we've been working on to address a particularly important societal problem, which is reducing food waste. And so this talk will be about both sides of, we'll cover both themes, both core, we'll talk about core machine learning research in uncertainty estimation, and then I will also talk about how this research could be translated into the real world via this company, Afresh. And I'd like to preface this talk with just a few thoughts on where AI has been coming from in the last several years and where it's heading. Obviously, in the last decade, AI has completely reinvented itself, and it has gone from what I think was maybe 15 years ago or 20 years ago, more of a relatively obscure academic field, to something that is now clearly an everyday technology. So we've had big breakthroughs in neural networks with the AlexNet moment in 2012. And since then, these technical innovations have found themselves in exciting new technologies, for example, in self-driving cars. We also have access to a lot of tools for building these systems, tools that we didn't have several years ago. And there's also a lot of interest in learning about machine learning. Currently, you can give yourself almost a master's degree by just taking a lot of courses, a lot of free, high-quality open courses online. So the access to AI knowledge has really has been greatly democratized in the last few years. And one interesting question to ask is, where is AI headed next? My personal thought is that some of the most important applications of AI, and maybe some of the biggest breakthroughs in applications of AI, will come in areas such as climate change, healthcare, reducing inequality, fighting disinformation, building more sustainable systems. These are societally important problems, and I think that now that AI has matured as a technology, it is poised to have a massive, massive impact in these areas. In fact, I think we're already starting to see some of this impact with new technical developments, such as DeepMind's solution to the protein folding problem. There's been a lot of exciting work in AI for drug discovery, and I think we're just going to see more and more of this over the next several years. And so this talk will be along this theme, and I would like to talk in particular about how AI can be applied to one important problem in sustainability. And in addition to talking about the technical and the research aspects of this problem, I also want to tell you a story of how these AI technologies can be taken into the real world and how we did this via a startup. So first of all, what is this societally important problem in sustainability that I've been mentioning? The particular problem that I want to talk about, that I want to focus in this talk, is the problem of food waste. Food waste is a huge, huge problem for society. In fact, in the US, according to various estimates, between 30 and 50% of all the food produced is currently being discarded. So if you take the food that is produced at the farm and the food that ends up going to consumers, along this path, about 30 or 50% of all the food ends up being discarded. This is a massive, massive number. It is a massive financial loss. It represents about $400 billion in terms of losses to the US economy, which is about 2% of US GDP, just to put this in context. And at the same time, while we're having these massive losses, about 1 person in 6 in the US at least has some form of food insecurity. So that represents about 50 million people in total that have some form of insecurity while all of this food is being wasted. I'm going to cite a lot of numbers in this talk, and most of them are coming from a particular resource called ReFed. ReFed is a large nonprofit consortium that is dedicated to looking for solutions to ending food loss. And they produce a very high quality resources that quantitatively measure the problem of food waste. And if you're interested in learning more about this problem, you should definitely look at this resource. Again, in particular, I'm going to be citing a lot of facts about food waste that have been compiled by ReFed. So most numbers are coming from there. Now, in addition to being an important economic and social inequality problem, food waste is also a massive, massive environmental problem. Creating all of this food that ends up being unused puts a massive strain on the environment. Again, just to give you some numbers, in the US, food waste would account, or the resources that are used to creating food that is wasted end up contributing something around 4% of US greenhouse gas emissions. 14% of all fresh water used goes towards creating food that is wasted. 18% of all cropland is used towards wasted food. And food is a massive component of what ends up in landfills. In fact, I would also go one step further and mention that food waste is a massive climate problem. Creating food that is wasted is a massive driver of greenhouse gas emissions. In fact, one statistic that is particularly striking is that if food waste was a country, then it would rank third in the world by greenhouse gas emissions. It would rank higher than countries like Russia or India or Japan by the amount of greenhouse gases that they generate. So by reducing food waste, we can also have a massive impact on climate, and we can hope to meet our climate mitigation goals, the goals that we need to meet in order to stabilize the climate crisis. So food waste is an important societal, environmental, and climate problem. This begs the question, what can we do to mitigate food waste? And in particular, why is there food waste and where does it occur? Again, according to this industry consortium called ReFed, a large percentage of food waste occurs at the consumer-facing stage and downstream. By consumer-facing, I mean things like restaurants, grocery stores, and then downstream, everything that finds itself in homes. So about 70% of food waste occurs in this sector of the supply chain. And again, just to give you an impact of an idea of the impact that food waste reduction in this sector of the supply chain can have, only a 25% reduction of US grocery food waste could eliminate tens of millions of tons of greenhouse gas emissions every year. It could conserve billions of gallons of water, and it could recover tens or hundreds of millions of meals every year. So tackling this problem in this sector of the supply chain is a massive opportunity for social good and for improving the sustainability of our food system. So we know where food waste happens, but why is there food waste? Why is this system inefficient? Again, I will refer to ReFed, and in particular, ReFed has a very interesting interactive database, which they call the solutions database. You have the link here at the bottom. And this resource ranks different solutions or different actions as in terms of their various impact on reducing food waste. And this is the rank list of the top solutions that are believed to have the most potential in mitigating food waste. And if you look at these solutions, well, you see things like enhanced demand planning, intelligent routing, markdown applications, better transit time when shipping goods from, let's say, a warehouse to a store. So these problems have the flavor of operations research problems. These are industrial automation and industrial control problems that are very solvable using the kinds of technical tools that we have in machine learning and AI, right? Again, we have things like demand planning, routing. These are supply chain inefficiency problems that could be naturally addressed using the tools that we have, which are tools like machine learning, optimization, planning, reinforcement learning. These are techniques that I will argue in this talk have a lot of potential for reducing food waste, and this is something that some of our work and research has tried to address. So just to give you an idea of where these inefficiencies are coming from, and an idea of why this consortium believes that greater automation and greater planning can significantly reduce food waste, let me give you this example. So what you see here on this picture are so-called they're called ordering sheets. This is a pen and paper workflow that is used at a very large grocery chain to plan their internal operation. So these are actual pictures that were taken at a company that is making billions of dollars in revenue and that has hundreds of stores across the US. This is a very large company, and yet they're using this highly inefficient pen and paper system to plan key aspects of their operation, such as their warehouse management, their store inventory management, their price management. The systems that are used in this area are still highly antiquated. These particular sheets that you see, they're called ordering sheets because every day a person in the store uses this pen and paper system to determine how much different items the store needs to stock in order to meet demand, but without ordering too much, because if they order too much, then the food might spoil. And every day, this person, who is, by the way, not a very technically sophisticated individual, this is the same person that stocks the shelves, that helps you find the food items that you're looking for. Part of their job is to also use this paper system combined with their personal intuition to decide how much to order of every item that is in the grocery department or in the produce department of their store. Obviously, this is a very difficult problem for a human to solve. They have to make these ordering decisions for hundreds of items while accounting a lot of external factors such as weather, holidays, seasonal patterns in demand. They have to factor all of these different features in their head and make ordering decisions for hundreds of items. Obviously, this is a very challenging problem to do for a human, but it is a natural fit for what machine learning can do. And so by increasing automation, by applying AI to these antiquated processes, we can have a significant impact on improving supply chain efficiency and reducing food waste, which is this massive problem for both society and the environment. So in this talk, I will tell you about some technical ideas in machine learning that can find themselves in supply chain control algorithms that can be used to solve some of these tasks that I just mentioned. And also, I will talk to you about how we can how this technology, based on how some research in this topic that we did at Stanford, ended up being incorporated into a startup company called Afresh, which came out of our research. So Afresh is a project, as I said, it came out of a collaboration at Stanford between the computer science department and the business school. Initially, this idea was identified in around 2017, and based on some early work exploring both the market and the business side and the technical side, our early team came to the conclusion that this is a problem where we could have some real impact by taking some of our research and creating a company out of it. This was around 2017, and then since then we have gone on to conduct initially smaller but then increasingly large pilots and partnerships with food companies, in particular with supermarket chains, and we went from a research idea to creating and deploying a system that is currently running in about 2,000 locations across the United States, and that processes about 10% of US produce volume in terms of sales. So the system is being used for automating about 10% of U.S. Produce volume. So this was an idea that went all the way from research prototype to something that is being widely used in enterprises right now in the US. So, okay, what does Afresh do? What is the solution? And how can machine learning help create this solution? And what are the technical ideas in machine learning that are needed to make it happen? The specific solution that Afresh is building is essentially a digital version of these sheets that you saw in an earlier slide. From the point of view of the users of this system in the real world, from the point of view of real world companies and users, we are replacing a pen and paper system by a digital one that still has a similar interface, but that runs on a tablet. However, the crucial piece of this system is a machine learning engine that lives in the cloud and that computes decisions for how a company should operate its store or its warehouse or its truck fleet. It is using intelligent systems, it's using AI to make better decisions and then surface them to the users via this type of interface. And so the kind of most interesting technical aspects here are within that machine learning engine. Now, one way to describe what this machine learning engine does is inventory control. We all know about the control problem in machine learning. You can envision the control problem. You can envision the problem of controlling a robot, but similar problems in control also arise in industrial automation, where, let's say, we might want to control a factory or some kind of machine, or we might want to control decisions within a supply chain. That is a classical planning, optimization, operations research, machine learning type of problem that is a really good fit for techniques that we have in AI. And I'm going to use the words inventory control to define this problem. Now, specifically, this problem of inventory control can be framed as a classical model-based control or model-based reinforcement learning type of problem. The reason I'm saying this is that we can formulate the problem as having two main components. One main component is a probabilistic model of the future, which, based on all the historical data that we can collect for what happened in the supply chain, these can include past sales, past vehicle travel times, expiration events, any kind of data that we have historically, we can use that to build a predictive probabilistic machine learning model of the future. And this model predicts a probability over everything that is still unknown in the future. One of the key unknowns is how much of a different item will sell at a particular location. So demand is obviously something that we might want to model, but you can envision this as being a model of anything that you would need to make a decision. So maybe truck travel times, or the state of an item in terms of its shelf life, the shelf life of an item that is circulating through the supply chain that might be unknown, and we might want to model this. So anything that is unknown, we try to predict it. And then there is a second step called a planning step, which uses these predictions to determine what are the best actions to be done, either by somebody in the store, like you see in the picture, or by somebody in operating a warehouse or operating a truck, or any kind of decision that needs to be done in the supply chain. We try to compute it using a planner, a model-based planner, because it is using our probabilistic model. And so this entire framework is what we normally in machine learning refer to as model-based control, right? And then the planner surfaces decisions which are reviewed by a human, and then this forms a loop that repeats itself every day. Every day new data comes into the system and new decisions are being generated. So hopefully now you're starting to think you're starting to have a better picture of how we can translate how we can take what we know of machine learning and apply it to a setting where we can have an impact on food waste. So what are some challenges in building a system like this? First of all, what are some challenges in building this predictive component? Well, one challenge is a big data problem. The supply chains of these companies are massive objects. They might contain data about tens of thousands of items and how they travel between the warehouse and hundreds to thousands of stores, and we might have years of data. So this might generate billions of data points. We want to be able to effectively leverage all of this data to make really accurate predictions. But even though we have a big data problem, we also have a small data problem. For each item, we might have only a few data points on a particular in a particular location. So if we wanted to predict the sales of a particular item in a particular store, we might only have a few years of data for this item, or maybe even less than a year, so maybe only hundreds of data points. And we have even fewer rare events. For example, if we needed to predict how much of a certain item will sell in a certain store on a certain holiday, then that's only a few days of data. That's only a few. We might have only 3, 4, 5 data points. So at the same time, we have a small data problem for certain rare but very important events. And finally, one challenge for building this predictive component is how do we make the predictive component useful for decision making? The predictive component is not important in itself. What is interesting is how do we make this information, how do we make these predictions useful and actionable for downstream planning algorithms? And that might inform the way in which we want to think and reason about the predictive problem. Now, some of the high level, I'm going to talk about some technical details later, but first I just want to give you a high level, without going into all the technical details, let me just give you a high level idea of the solutions that could be used to tackle these problems. So obviously when we have a very large data set, that is a natural fit for predictive methods based on deep learning. And that's something that's important to, that has been important in our work so far. When we have these rare events, when we have the small data problem, that is a natural fit for multitask machine learning and even certain applications of meta learning. So even though we have only a few days for how a few days of data, a few data points for how a particular item might behave in a particular store, in a particular location, on a particular holiday, we can pool this data across many different stores, or maybe across non-identical but related items to increase the signal that our model has access to. And by deploying large deep learning multitask model, we can solve some of these small data problems. And finally, our thinking about our plan for approaching the decision-making challenge. Again, these are predictions that are needed for decision-making. Our approach there centers on using probabilistic predictions, which capture the full uncertainty of the model. And I'm going to argue in a few slides that these probabilistic predictions and a certain type of probabilistic prediction is particularly important for making good decisions. Now, obviously, there's also challenges on the decision-making side. Again, we need to take these predictions and have the planner produce actions that correctly account for objective and constraints. Objectives could mean a balance between, pure profit maximization and waste reduction, as well as real-world constraints such as delivery times or routing speeds. And these decisions often have to be made in a partially observed environment. We may not observe the full state of the supply chain. We might not observe the inventory, the shelf life. These are unknown variables that we either have to model or we have to come up with clever solutions for how to deal with them. And so again, our solution here rests on 2 pillars. One would be the use of model-based predictive control, this general family of algorithms that are naturally suited for solving these kinds of decision-making models. And then another pillar is human-in-the-loop AI. That might not be something that I have a lot of slides on in this talk, but all of these systems must still be used. They still operate with a human in the loop, and this by far gives the best performance because instead of replacing the human, we try to combine the strength of the algorithm, which has access to partial data, in particular one subset of the data, and the human, which has access to a different subset of the data. And we've many times observed that combining the two together by far gives the same performance. and it also requires certain thinking in terms of the algorithms and the interfaces that we want to use for this. So here I gave you an overview of a problem, a high-level technical solution to this problem, but there's also some interesting machine learning technical work that underlies this this solution. As I mentioned earlier, we did some interesting research at the intersection of machine learning, sustainability, ballistic modeling, model-based control. We did this research in around 2018, 2019, 2020, and we published a few papers out of this work. So here are two screenshots of two ICML papers that I really like, that I think are these are some of my favorite papers. And these papers describe some technical ideas in machine learning, which I think are both novel and important to get the best possible performance on this applied problem that I just mentioned to you. So I'd like to spend a few slides diving a little bit deeper into the technical details, and then after that I'll conclude by just again an overview of some real-world examples and with a few anecdotes of how the system works in practice. But the next few slides that might be a little bit more technical, I want to give you a few snippets of some interesting technical ideas in machine learning that I think are important for making these supply chain control algorithms work very well. So the main question that we asked ourselves in our machine learning work is the following. Well, I guess there's a question, and we started with the observation that what is really important for accurate control and accurate decision making in machine learning under a model-based planning framework, what is really important there is a good understanding of model uncertainty. This is a toy picture from one of our papers that illustrates why uncertainty might be important. Here we have this toy idealized example of a self-driving car, and the car is perhaps using a model of the world to determine what will happen if it makes certain actions, if it turns the wheel, for example. And here we have two ways of representing the knowledge that the car has about the outcome of its decision. So let's say that we turn the wheel by a bit. The car might use a predictive model to predict where to go next. And here we have two possible models, the green one and the purple one. The purple one has a bad estimate of uncertainty, or it has at least a narrow uncertainty. It is being overconfident. So first of all, both the green and the purple predict the same mean. They predict that on average, if I turn the wheel, I will go in the same direction. But they have different measures of uncertainty. The purple one is overconfident. The green one better represents the uncertainty of the model. And you can see that certain bad events, like hitting the pedestrian, are much more likely under the true model than under the overconfident model. And so if our uncertainty estimates are wrong, we might accidentally have really bad adverse events that will happen to our system. We want to avoid these events in any sort of planning system by having an accurate estimate of predictive uncertainty. And so this is a high-level idea. This hopefully should just convince you that measuring uncertainty is important, because if not, bad events will happen. But what kind of uncertainty specifically do we need for decision making? Our work is grounded in classical statistical theory on proper scoring rules, which argues that there are two types of uncertainties that are particular, or well, I guess there's one particular characterization of uncertainty that is especially important for decision making. So if you were to take, now I have a few formulas here, but the high level idea is that if you take most of the objectives that we're currently using to train our machine learning models, such as the log likelihood objective, these objectives naturally, well, first of all, they ask the model to produce uncertainty. These are objectives over probability distributions, but they're asking for two specific aspects of uncertainty, two particular dimensions along which we can measure a predictive probability. One of them is called calibration. Calibration means that if I were to predict a probability or a confidence interval, something like a 60% confidence interval, then this interval should contain the true outcome about 60% of the time. So obviously this is something that we would want, and obviously an ideal predictive uncertainty should satisfy this property. And then the other property that is important is something that I will call refinement, or I've sometimes used the word sharpness to define this. Refinement is a measure of how narrow or wide are these confidence intervals. Ideally, we want to have confidence intervals that are calibrated and that are as narrow as possible. And in particular, the ideal forecast is a calibrated interval that is maximally narrow. In fact, it's a delta function on the true outcome that is literally the best possible prediction that we can have. It is 100% confident and it is 100% correct. But in practice, we're not able to achieve a perfect forecast. And so anytime we optimize a machine learning model, we have to strike a balance between these two objectives, making our intervals narrow and having them be calibrated. And in fact, most of the objectives that we use in machine learning, such as the log likelihood, naturally decompose into these two terms. You can think of this as being a decomposition analogous to the bias variance decomposition or analogous to the aleatoric epistemic uncertainty decomposition. This is another decomposition that decomposes the objective in calibration and refinement, and it precisely identifies the two criteria that are important for a good forecast, for a good probabilistic forecast. So these two criteria are important, but one natural question is, are they equally important? Is one of them more important than the other? And the answer in our work is that yes, we argue that the calibration term is more important than any other term in this decomposition. Calibration is more important than refinement for making decisions. So in this context of model-based decision-making, if we had to choose between either a really narrow but overly confident interval or a wide interval but that might have less certainty about it, we want to choose the wide interval if it's more calibrated. A calibrated prediction is important for decision-making. And so in one of our papers, in the ACML 2019 paper, we studied this problem more formally. In particular, we studied it in the context of model-based RL, and in particular, we looked at estimating the value of a policy under a particular model of the world, in particular, a model of the transition dynamics of an MDP. And we showed that having a calibrated estimate of the true dynamics is a sufficient condition for being able to estimate the value of a policy. So we might have a model of the dynamics that is imperfect, but if it is calibrated, it can give us a more accurate estimate of the value of a policy. And in practice, if we were to enforce this property, we would obtain better, more accurate decision-making systems. So we argue that the calibration aspect is important, but then the question is calibration something that our models already have? And the answer is no. In our other paper, well, in our ACML 2018 paper, we argue that if you take most machine learning models, especially models based on neural networks, and you ask them for confidence intervals using maybe a classical method like variational dropout, if you're familiar with that, but if we use a lot of the standard methods for getting uncertainty out of a neural net, we see that these uncertainties are wrong. They're typically overconfident. Here, this is an example from a small off-the-shelf Bayesian neural net that shows that confidence intervals are actually significantly overconfident. Here, the green zone is the 90% interval, and it only contains 2 points out of 10. So it's clearly overconfident. And in our work, we proposed various techniques that can improve these estimates, and they can provably yield calibrated predictions of machine learning performance, of predictive machine learning. It can yield calibrated predictive machine learning intervals. So here, after applying some of our algorithms, we could get a model that we could get something that looks like what you see on the right, which is a green interval that contains correctly 9 points out of 10. And this can be done provably in a lot of interesting settings. And in particular, the flavor that these algorithms have are that they take a baseline machine learning model that could have been trained in any way, in any sort of way, either using maximum likelihood maximization or perhaps even using a non-probabilistic objective like the hinge loss. And then we create this algorithm such that we create this additional model R such that we call R the recalibrator, and the recalibrator has the property that when we compose R with F, the resulting model will be calibrated. And in our work, we show that there exists a true base optimal form for what R is. And in particular, this base optimal form is a density, which you see here on the right in the context of binary classification, where we only output a single scalar probability. This would be the ideal recalibrator. And so therefore, we can reduce the property of enforcing calibration to learning this density. This is here, boldface P is the data distribution, and this ideal density is the true probability of the label y equals 1, conditioned on a certain predicted probability. If we can learn this mapping, this is a well-defined mapping that is derived from our data distribution. It is also only a two-dimensional object. So, well, in fact, it's a one-dimensional density estimation problem because the only variable here is P. And if we can solve this one-dimensional density estimation problem, then we can achieve the property that we're looking for. So this just gives you a high-level flavor of what these algorithms look like. And again, just to give you an idea of why this is important, this is not a purely academic research into the properties of probabilistic predictions. Enforcing this property actually helps with in decision-making scenarios. We tested this first in several standard benchmark environments that are widely used to benchmark control algorithms. And here we have a result with 3 different methods. We're comparing, so here we're using this standard benchmark called the half-cheetah Mujoko environment, where we're comparing 3 algorithms. We're comparing what was at the time a state-of-the-art model-free algorithm called soft actor critic, and we're comparing this to a model-based control system that uses an uncalibrated model, that is the uncalibrated baseline. And then we're using the exact same algorithm, but applying our additional recalibration technique on top, which is the result in green. And we see both in half-cheetah and in other standard Mujoko environments, consistent improvements from switching to a calibrated predictor. And also we're able to achieve the performance of a model-free algorithm. So soft actor critic, if you let it play for a very long time, it gets to the dashed line at the top, but it requires a lot of data, requires a lot of interaction with the environment. These model-based algorithms are much more data efficient, and so they're able to reach the performance of a model-free algorithm using much, much fewer steps. And then again, this works in other environments as well. And finally, we also tested this algorithm both in simulation and in real-world systems for inventory control, where you can formulate inventory control as a control problem in the following way. There's an inventory position. The state changes because of sales, spoilage, and shipments, and all of these things. So the state changes over time, and our goal is to optimize reward, which might be either waste or revenue or any sort of objective. And when we use a calibrated model with an optimizer that's based on approximate dynamic programming, we're also able to significantly reduce waste, stockouts, and we get significant improvements in control. So this was an overview of some of the technical ideas that we worked on to make this system happen. I realize we're almost out of time. I think we were supposed to end at 1:30, so I'll just quickly end with a few highlights of how all of these algorithms work in the real world. I'll maybe just do, well, first of all, again, as I said earlier, the system was deployed over the years. I guess in the 5 years since we started doing this research, the system has been deployed at a large scale. It has been deployed in over 2,000 stores across the United States, which is about 10% of the market. And here I just have one fun anecdote of how the system worked in one store during an early pilot. So here what you see is a curve that measures waste. It measures cumulative waste. So every day something goes into the store, something is sold. So we just track that. We initialize a counter at 0, and anytime something goes into a grocery store, we add it to the counter, and when it's sold, we subtract it. And we see that over time, this counter increases because what is sold is less than what is shipped, and this delta is what is wasted. So the curve here measures waste, measures cumulative waste. And so as we go up, there's more waste, and we want to keep this curve flat. Our objective is to keep this curve flat. We ran an experiment. So this is historical data in an early pilot. And then we turned on our system in the store, and we immediately saw a stabilization in waste. Waste remained flat. But then something happened. The operator of the store, they got sick. They had to leave. They had to give the system to their assistant. And their assistant didn't trust our system. They decided to override most of our recommendations. So they just ignored our recommendations. And immediately in that week, the waste increased. We had a big jump in waste as soon as the person left. And then when they came back, we reactivated the system. They started following our recommendations again, and the waste stabilized. This was a fun A/B test, and an unintentional but fun A/B test of using our system that highlights in a particular way how it can affect waste and performance. And again, this technology has been deployed in the real world. It has resulted in waste reductions of about 25% across different customers. And these waste reductions have had a real impact on reducing food waste. In particular, we estimate that this is out of date, actually. It's more than that. But as of last year, 20 million pounds of food waste have been averted by deploying this system, and now it is much more. So again, I just want to conclude by summarizing some key ideas of this talk. I think that machine learning and AI is poised to have a massive impact on problems that are important to society, such as sustainability. Within sustainability, there's this massive problem of food waste where AI can have a big impact. And in some of our research, we have explored ways in which machine learning can be used to tackle this problem. We came up with some new technical ideas in machine learning based on uncertainty estimation for decision making. We ended up taking this research into the real world via a startup company, and this research ended up having an impact into on this important real world problem. So I'll end here, and again, I really want to thank you for inviting me to give this presentation, and thank you for the efforts that the organizers have been doing in helping Ukraine. I think this is a very important cause, and I'm really grateful to have the opportunity to contribute towards this cause by giving this talk. Thank you.
Hi, thank you very much. Dima, I think we cannot hear you still. Okay, no, I think it's not working. So thank you very much for the talk, for this very interesting talk. Indeed, it's a very interesting topic, and I totally agree that it's a very important, from the social and environmental point of view, important challenge for the future. We're gonna read some questions now from the audience. So the first question is from Melisante. For the inventory problem, have you also thought about nudging consumers towards more sustainable products, and how can we incorporate this constraint in the model, seasonal produce, etc.?
Yeah, definitely. There's a lot of opportunity to nudge consumers towards better behavior. Part of our thinking is that, well, I guess we're not in the consumers' homes. It would be really nice. I think there's a lot of impact that could be had there if we could also kind of push certain decisions to the consumers. The best that we can do for now is to improve the quality and the shelf life of the items that are in the supply chain before they get to the consumers. And by providing them items with a longer shelf life, then they last longer in their house, and therefore there's also less waste on the consumer side. That is our thinking so far, but we would definitely love to have more impact in their in their homes as well.
Thank you. So, second question from Alexandra Volokov. Thank you for the great talk. Could you elaborate a bit more on the machine learning methods that you are using for uncertainty estimation and how you calibrate them?
Yes. Let's see. So for the full details, I would say some of the papers here. We had a few papers at ICML 2018 and 2019. First of all, I will only give you an imperfect or a high-level overview of this. For the full details, it is best to look at these papers. The high-level strategy that we've been using is something called recalibration, where the idea is that we can have an existing predictive system, which can be a neural net trained using maximum likelihood, and then this neural net can produce predictions using something like variational dropout, using deep ensembles. There's a few standard methods with for doing uncertainty quantification, and they all fit within our framework. But you can just think of there being some system that is a black box and it produces predictive uncertainties. And in our paper, we, first of all, empirically and theoretically in different ways, we argue for why these uncertainties don't satisfy this calibration property, which we find to be important for decision making. And we propose a technique that provably enforces this property. And we argue that there is another distribution, which we call R. This is in the binary classification setting. So we predict, well, I guess in the binary classification setting, we have an outcome that's either 0 or 1, but it extends beyond that. But let's say we only have an outcome that is 0 or 1, then the forecast is a probability for between 0 and 1. And you can think of a recalibrator as being something that remaps these probabilities. And we show that there exists in various papers, this one, and there's a follow-up one, we show that there exists an optimal R, which is guaranteed to have this good calibration property, and that, it is probably guaranteed to have it, and there is a base optimal form for R, which is essentially this formula. And so the problem reduces to estimating this base optimal recalibrator. And we do this via modeling density estimation techniques. So I guess you know P, you know Y. So in this case, estimating this density can actually be reduced to a supervised learning problem. And there is a choice around which density estimator to use. But essentially, the high-level answer is that there is a recalibration process. There is a base optimal recalibrator, and estimating this base optimal recalibrator can be reduced to a supervised learning problem. I don't know if that's the right level of detail for this question, but that's my answer.
No, thank you very much. And now Dima wrote us a question he'd like to ask. Unfortunately, his micro is not working. But concerning A-Fresh, at what granularity is your model asking predictions? For instance, do you have a separate model for each product, or you have a more general model like store level?
Yeah, and I think you can think of granularity in different ways. There's time granularity, and then there's, if we focus on inventory, then there's granularity in terms of stores and in terms of items. So we perform inventory control across hundreds to thousands of stores and hundreds to thousands of items. And then there's also a time dimension to this. In the time dimension, the frequency is daily. So it's not a super fast control problem. It's a slow problem where the actions are made every day. Along the item and the store axis, I told you those are on the order of hundreds or thousands, but I guess the question was, are these made using separate models or a single model? And this is what I wanted to argue here. So if you multiply all of these decisions, that's a lot of decisions. There's thousands to tens of thousands of items across many, many stores. So that's a big data problem. But there is also a small data problem, because if you narrow things down to only one item in one store, there's not that much data. There's only hundreds of data points because we typically have a year, 2 years, maybe 3 years of data. And in particular, there's also rare events. Like, for example, we would like to do this for Christmas Day. We'd like to have accurate predictions on Christmas Day or New Year's. And that makes it that there's even less data points. And this is why it is important to use a large model that is multitask. You can even think of this as, there's even room for meta learning, because sometimes you start making new predictions on new time series, which you haven't seen before. Yeah, so the multitask problem, essentially using a large multitask model is an important part of the solution to this problem.
Thank you very much. And now the last question is a non-technical question. So how willing the retailers are to use AI systems in their work? Do you get them really involved in the process?
Sorry, and the first part was how to get retailers involved in using this work.
Yeah, how willing they are to use AI systems in their work?
Yes, so that's a good question. I think taking this work and deploying it into the real world, it's a very complicated process. It's more complicated than the research, to be honest. It requires a lot of people to agree to do things. And retailers is a very broad term. There's a lot of people that you could call retailers, and there's different levels of engagement that you need from all of these from all of these parties. Ultimately, if we want to use this system on a large scale, we have to talk to big companies, and then there's executives, vice presidents at these companies which need to be convinced. They care more about the numbers. They actually care about their profits, but they also care they care about food waste as well. They actually have a lot of initiatives around reducing food waste. It is actually a very high-level public priority for a lot of these companies. So they do care about the environmental aspect, and they of course care about saving money by using a system like this. So getting them involved, it requires work. It often requires numbers, practical results, previous deployments, pilots. So that's one type of engagement. One type of engagement we have, and one type of convincing that needs to be done. And then another convincing is who are the individuals that are day-to-day using this system. And this is also a really interesting question. I guess as I mentioned, part of what we do is to get a person like this in a store to use our system. And these individuals, these people, some of them are very young. They're just out of school, and this is their side job. Some of them have been doing this job for tens of years. They might not be the most technologically sophisticated user. Not everybody might have a smartphone even. So it definitely takes effort to understand them, to create a tool. So now we're going into something that is not a machine learning question. I guess they're not that exposed to the machine learning. What they see might be an interface like this one, and it requires a lot of careful thinking around creating an interface that they feel comfortable with, that still mirrors their original process. There's a lot of other considerations in terms of speed and then the kind of data that is surfaced that is important to them. So these are all, of course, super important consideration. It requires a different type of effort to get buy-in from them. And I would also add that uncertainty quantification, which we talked about here, also has an important role to play, because it is easy to lose the trust of these users by having a faulty system. And so if some of these decisions that are being surfaced to them are wrong, their trust could disappear. That would be very bad. And so uncertainty quantification, knowing what you know and what you don't know, is important for deciding what to surface here, and that helps to build trust with these kinds of users, because it helps the system be more accurate and not surface untrustworthy untrustworthy outputs, if that makes sense.
Yeah, so very much. I hope you can convince them and that you can bring the project to even like new places, new countries, because I think it's very interesting. As I said, I think it's a very important challenge that we'll have to face in the future. So thanks to you. Thank you very much for everyone who attended the talk. You will find the recorded video after on our YouTube channel and here on Crowdcast. And I invite you to help us with our last, giving our last push to our contest.
Hello.
Hi, Dima.
Hello. Oh, hello. You.
Yeah, we can hear you now. Do you want to say? Yeah. I know we cannot hear you anymore. I'm sorry. I'm sorry. But yeah, thank you very much. Oh.
I'm sorry. It's also the first time we use Crowdcast, and it's behaving a bit weirdly with my headphones. I don't know. But Volodymyr, thank you very much for agreeing. It was a really great talk, and it was really nice to see the real world application and.
Yeah, and again, I'm really grateful for that your team have invited me, and I'm even more grateful for all the work that you're doing in organizing this conference and helping Ukraine. And thank you for letting me help you, basically.
No, thank you, Volodymyr. And also, you have a really great course on YouTube. I actually, first time I learned about you was actually there, and thank you for doing this too. And
yeah, that's awesome. Maybe I can do like a quick preview. There's a new version that's coming in the next few days. So this is the first time that I'm announcing it here.
Oh, cool. Yeah, actually, it's a really great course because you give real examples there. Like unlike some other courses, you have really Jupyter notebooks that can be replicated, and all your experiments can be. But basically, students can follow what you do and see the results in practice, and it's really valuable. So yeah, everybody should definitely check out your course.
Awesome. I really appreciate it, and we're going to try to make it even better. Hopefully the next iteration is going to be even better and fix all the bugs from the previous one, and we'll just try to make it better.
Awesome.
Yeah, so thank you. Good luck with the new step of the project, and thank you very much to all of you.
Thank you. Thank you.
Thank you, Volodymyr.